Good evening, everybody. Happy St. Patrick's Day. Yes, it is my birthday, so thank you for the birthday wishes, Cindy, and everybody. Um, so today we are going to cover the Chapter 8 project. Um, so Next week, don't forget, on next week on Tuesday, March 24th, we're going to do our candy project. For the candy project, you're going to need to make sure that you've purchased some M&Ms or some Skittles. If you don't want to purchase any, let me know and I will direct you to a site where you can select where it'll do the randomization for you. But I've already bought mine, so uh, yeah, hopefully the family doesn't eat them before next week. So anyway, um, you'll need somewhere between 3 to 16 ounces of M&Ms, and same for Skittles. Okay. But today we're going to look at the Chapter 8 project. So if you click in Canvas on the Chapter 8 project, exploring a sampling distribution. There's two links in there. One for the Google document where we're going to put our answers, and another one for the sampling distribution applet, which is in StatCrunch, but you don't need to sign into StatCrunch. So, uh, yeah, I'm going to drop the links in the chat for you, though, so you don't have to go search for them. So here's the link to the Google document, and here is a link to the StatCrunch applet. Yeah. Um, okay, so starting off with the Google document, we need to go to File, make a copy, right? 26. Okay. And I'll save this somewhere. Put it in your, I'll put it in my drive, right? Make a copy. All right. Okay. The link to the applet is also here in the Google document, but I already dropped it in the chat, so you don't have to go search for it. So set the applet so that the population is bell-shaped, copy that and paste the mean, median, standard deviation. Okay. So before we jump into this, I want to take a look at it. So there's 4 parts. So there's part 1, part 2, part 3, and part 4. Okay. Um, so parts 1, 2, and 3 are pretty much the same. Part 1, we are going to have a normal distribution and we're going to take some samples from it and we're going to jot down a bunch of things and we're going to increase the sample size. Okay. And as we do that, we're going to see what happens. Do things increase or decrease significantly? Part 2, we're going to do the same thing with a skewed right distribution. And then part 3, we're going to do the same thing with a skewed left distribution. And then part 4, we're just going to kind of wrap it all up. Okay. So this project's a little repetitive, but that's okay. Because it hammers home the point, which is in chapter 8, we are going to be talking about the central limit theorem. Okay. The central limit theorem is a very important part of statistics. I mean, it makes sense because it's central. It's important to statistics. So um anyway, so what the central limit theorem says in chapter 8 is that it doesn't matter what shape your distribution is. If you take a bunch of samples and look at their means, that distribution is normal, okay? Which is a bit of a surprising conclusion. And so, yeah, so we're basically exploring that, okay? If none of that makes sense, that's okay. All right, we're gonna talk about it as we go, okay? But up here at part one, in my opinion, is boring. We could, it doesn't really tell you much. Okay. Part 2 is where things get exciting. Okay. So part 1, uh, we are going to write the mean and the median and the standard deviation of our distribution. So now go over here into the StatCrunch, and we have this distribution at the top. This is the population, okay? So this population is normal shaped, okay? So I don't know what we're measuring. You know, when we looked at the Chapter 7 project, we were looking at home runs, and we said that the home run distribution for distances was pretty much a normal distribution, okay? So each dot in here is uh or not each dot, but like each dot on the graph for the scatter plot was a home run that was hit. So there were like 6,000 home runs, right? That was our population. And we drew a histogram, and the histogram looked like a normal curve. Okay. Or maybe it's something else. Maybe we're looking at average height or average weight of people in the US. And so each data point is a person, and we can build a histogram of their height or their weight. And that's pretty much going to follow a normal curve as well. Okay. Um, Now, the population is huge. Okay. So if we were going to look at, what's the average height of people in the US? Well, that's going to be impossible to get because there's like hundreds of millions of people in the US, right? If you needed to measure every single person, that's going to take forever. It's going to be, very expensive, and it's going to be hard to do. Okay. There might not even be people that want to do it, right? So, if we were looking at the world, like there's people who don't even have contact with the outside world, right? I mean, think about back when COVID-19 was around and we had a vaccine that could help people stay healthy. Did everyone take it? No, not at all. So it's practically impossible. Yes, Nathan, it's practically impossible to find the height of everyone in the US. So because of that, we have to take a sample. Okay. And when you take a sample, maybe you have like 100 people or 1,000 people or whatever. Um, and when you take that sample, you can measure the average height of the people in the sample. Okay. So Corbin says, I'll give him $10. And I think, well, so that's going to cost you like $3 billion because there's like 300 million people. So it is not cheap. So, okay. Anyway, so you don't need to do this, but in the upper left, if I click one time, it will take a sample. It'll grab two people from my population, measure their heights, and then take their average. The average is right here in the middle, and it'll drop it on this green dot down here. So the top is my population, okay? The middle is my sample, and I've got my sample size currently set to 2, okay? So we'll leave it at 2 for now. And then down here is what I get for the mean. Now, if I do that again, if I click one time, I get two different people and measure their heights and take the average, and I get a new dot, new green dot down here. So if I do it again, right, I can, keep taking samples. Wow, that one's way over there. Okay. And so I keep getting a bunch of green dots here, right? Okay. Now, for the project, it says, oh, I completely skipped number 1A. So for the project, was I doing that? How was I doing that? You don't need to do that, but I was clicking the one time in the upper left. Okay. So you don't need to click one time, but you can if you want to see a bunch of dots sampled. So okay. So part A is asking what is the mean and the median and the standard deviation of our population. So in the upper right, I have a mean of 25, a median of 25, and a standard deviation of 5. So that's what I'm going to put right here. Okay. Standard deviation of 5. Okay. Part 1B, obtain 1,000 random samples of size 2. Copy and paste the values of their mean, their standard deviation, and describe the shape. Okay. So I don't want to have to keep clicking this 1,000 times, right? That's going to take forever. So there's a button right here where you can do 5 times, but even that's going to take forever. So let's hit reset in the upper left. We'll hit reset. We'll start over. And there's a button here where it says 1,000 times, and click on that and see what we get. Okay, so reset and then click 1,000 times. Okay, and what it's done is it's selected 2 people 1,000 times. So it basically selected 2,000 people over and over and over. And each time it grabbed a pair of people from our population and grabbed a sample of 2 of the maybe they're not people, whatever we're measuring. Okay, I'm using people. Let's pretend that this is, the population is the height of all the people in the US, right? So, and then it takes the mean and puts a green dot, and we get a whole bunch of different green dots, right? So down here is our distribution of sample means, okay? So you're gonna hit, I'll do it again. We hit reset, click 1,000 times, and this one in the middle is just the last one that was taken. So this middle one, you don't need to look at this. This is just 2 people that they selected on the 1,000th sample they took, right? Um, all of these green dots down here, though, they have a mean and a median and a standard deviation. Okay. Now your numbers will be slightly different than mine, and that's okay. All right. Part of the fun of the projects is you get to play with your own data and you get things that are a little bit different than me. Okay. And you get to, see what I get, see what you get. Okay. Um, so yeah, so over here let me see if I can shrink this so I can see both. Okay, so for part 1B, I'm going to put my mean. So my mean is 25.08. Okay. I'm just going to do 2 digits after the decimal. It doesn't say how many we need, so that's good enough. Standard deviation, mine is 3.52. So what mean did you guys get? Did you get like a 24, 25, 26, 28? Okay. So Gabby, make sure you're looking at the mean down at the bottom, not the one in the middle. This mean right here in the middle, that's the mean of the sample. Okay. We are looking at down here, this green distribution, its mean. Okay. So Gabby says, oh no, she got 25.12. Okay. That seems much more reasonable. Okay. Um, and then standard deviation, I got 3.52. What'd you guys get? So it looks like everybody's mean is somewhere around 25, which is what it should be because the population's mean was 25. Isaiah's got 3.4, Gab's got 3.4, 3.7. Okay, those all sound good. Now, 3.6, that sounds good. All right. So my original population was normal. It was a normal shape. And I took a whole bunch of samples. I took 1,000 samples of size 2, so basically 2,000 people, did a bunch of averages, and I got this distribution down here. What shape is this one down here? Is it uh, very skewed left, slightly skewed left, very skewed right, slightly skewed right, or normal? What do you guys think? So my mean is 25.08. My median is 24.99. Those are extremely close together. Okay. If I was to reset this and run it again, I'm going to get these 2 numbers real close together. They don't need to be perfectly the same for it to be considered symmetric, for it to be considered normal. You'll remember in our Chapter 7 project, the home run distribution that we were looking at was not perfectly symmetric, okay? But it was when we were looking at the quantile graph, The dots were not perfectly lined up. There were a couple here and there that were off, but it was real close. It was a strong positive correlation. Okay. Doesn't need to be perfect. Okay. Because perfect is like a 100% correlation. We've never seen that. Right. So, I think this is normal. Okay. Mine is normally distributed. Yeah. So uh, I'm going to say normal. Normal is a specific type of symmetric, right? Symmetric could be uniform or there's other types of symmetric. Um, but a normal distribution looks kind of like a bell shape. Okay. It goes up and it goes down. Okay. Um, Now this is a boring result because we had a normal population. And so, of course, when we took some samples, uh, our resulting sample distribution is also normal. Okay. So Gabby, I would say, so I think that yours is normal as well, but if you put slightly skewed left or slightly skewed right, that's fine. Okay. Because this one might be off because a sample size of 2, there is some randomness, right? These are random samples, and so there's a chance that yours ends up being skewed. But let's move on to the next part, which is we're going to increase our sample size to a sample size of 5. So let's go back over here. Oh, I didn't want to do that. What have I done? Okay, don't click your population or you have to restart it. Okay. Okay. So right here on the right, we're going to change our sample size to 5. Okay. When you do that, it should reset everything. Okay. Or you can hit reset. Okay. But change your sample size to 5. Now, if we were to do a single sample, it's not selecting 2 people, it's selecting 5 people and then measuring their heights and then taking the average of them and putting the green dot down here, right? And if we did it again, here's another 5 people and they're, oh, I got the same average. Wow. Same average every time. Something's broken. Now it's not giving me a different one. Well, that was amazing. Oh, now it's only giving me that. Oh, okay. All right. Well, we just happened to get a couple that were at the same spot. Anyway, we're going to do that 1,000 times. So I'm not going to click the button 1,000 times. So I'm going to hit reset. I'm going to click 1,000 times, and there we go. Yeah, you change. So you'll change it. I'll do it again for you. You change this to 5. You hit reset, and you click 1,000 times. Make sure you click 1,000 times, or it's just going to be blank. Okay, and then you should end up with a green sample means distribution at the bottom. Okay, so Jordan, hit 1,000 times, and you should have what you need. Okay, so now that I've done that, my mean for this one, so make sure you're using the what's down here, okay? Not this one, okay? Not the middle one. The one at the bottom, I have a 25.08. So my mean is the same again, 25.08. It's not necessarily going to be for yours. You might have something a little different, which is fine. My standard deviation is not the same though. I got 2.22. And what do you guys think the shape of this one is? Yeah, it's still normal. Yep, you got it, Quinn. You had a normal population. It's not surprising that the sample mean distribution. Yeah, that sounds good, Gabby. Yep, that looks great. All right. And we're going to do it again, this time with a sample size of 10. Okay. So let's do it again. So change this to 10, reset, hit 1,000 times, and we'll record what we got again. So this time my mean is 25.00 and my standard deviation 1.64. And is it still normal? Yeah, it's definitely still normal. Okay. So your numbers will probably be different than mine, but I think your shapes are going to be similar to mine. Okay. And we'll do it again with a sample size of 30. Okay. Now 30 is the magic number, but we're really not going to see much change here So we hit reset, hit 1,000 times. My mean is still 25.00. Yours might be a little higher, a little lower. That's fine. Standard deviation 0.93. Is it still no? Yeah, it's still normal. Oh, okay. So remember, you're not just copying my numbers, okay? If you just copy my numbers, well, then you're not going to get any points. So I want you to type in what you get, okay? If one of your numbers is the same as mine, like if you get 25.00 for one of the means, well, that's totally fine. But if you get all 8 of these numbers are exactly the same, then, that's not right. That that means you were just copying. Okay. Now that we've done that, we're going to take a look at these numbers and talk about them. So for this bell-shaped population, as the sample size increased, what happened to my means? Did they decrease significantly, stay roughly the same, or increase significantly? Ryan says the same. Yeah, they stayed roughly the same. So I can't circle, so I'm going to highlight. So choose my highlighter. Oh, I'm going to do green. Yeah. Today is March 17th, so I'm going to highlight it in green. You can choose whatever fun color you want. That's fine. Um, yep, that sounds good, Gabby. For this bell-shaped population, yeah, that's still normal. Yep. As the sample size increases, the standard deviation, what happened there? So my standard deviation went from 3.5, 2.2, 1.6, 0.9. So decrease significantly, roughly stay the same, increase significantly. Kelly says decreased. Everybody agree, disagree? Yeah, Nathan says yeah. Yeah, it went down. Now, did it decrease significantly? I mean, it went from 3.5 down to 0.9. So that means it went down, it's 3 times as small. Like basically 3.5 divided by 3, actually divided by like more than 3. So if something drops by 300%, that is significant. Okay. So what I did was I selected the words I wanted to highlight, and then there's a button up here next to the text color. You can change the text color if you want, just however you want to indicate your answer, but there's a little marker and you can choose whatever fun color you want. You can do pink. I'm going to do green today. So, um, for this bell-shaped population, how does the sample size appear to affect the shape? So as my sample size changed, my shape was always still normal. So as sample size increased, the shape stayed normal. So, so that, as I said, is the end of part one, and part one is boring. Okay. Part two is where things get exciting. Okay. Um, I mean, maybe you're not excited. It's math. How excited can you get? But I'm excited. So, because this time we are going to do the exact same stuff, but we are going to do it on a skewed right distribution. So draw a very skewed right distribution by holding the left mouse button down and dragging the mouse over the distribution. The mean and the median need to be at least 2 points apart. Okay. So how do I do that? So let's go back over here and we'll hit reset. And I want to change my sample size back to 2. But this time I'm going to change my population. So I want it to be skewed right. So if you left click on the population, you can draw all kinds of crazy shapes. Okay. If you click and drag. So I want to draw a skewed right population. So I need like a big lump over here, and then I need a nice long tail going off to the right. Okay. And maybe make a little fat tail. Yeah, there you go. Okay. So my mean and my median need to be off by like 2. Here, I have a 14 and a 10, so that's a difference of 4, which is good. If I do you probably want to make your bump pretty small, because if I do this, if I do this, that's not going to work. My mean is 13.9, my median is 12.6. That's only a difference of 1.3. So you probably need like a one big bump over here and then a nice long tail. So now my mean is 14, my median is 10.9. That's a difference of 3.2. So that's good. Okay. Anyway, and the fatter your tail is, that'll make it easier to so get some outliers out here. That'll make it easier to make sure that they're far enough apart. Okay, so we're gonna write down what my mean and my median and standard deviation were for this. So now I'm recording my mean, median, and standard deviation from the top up here. So my mean here is 14.73. And my median is 11.06. And my standard deviation is pretty big, 8.93. Okay. Um, I haven't done the 1,000 thing yet. All I've done is uh made my population up here. So I'm recording the mean, median, and standard deviation from these top numbers up here for the population for part 2A. Okay. Part 2B is where we do the 1,000 samples. Okay. This sounds good. What's your median? You got to record your median as well for part 2A. Those are not two apart. You need to make sure that your mean and your median are more than 2 away from each other. So you need to make your population even more skewed to the right. So make a big bump on the left and then a nice big tail on the right. So, okay. So now that we've done that, we are going to come down here and we're going to do it again, where we do 1,000 random samples of size 2. Okay. So reset your sample size to 2, and then we're going to hit 1,000 times, and we get all of this down here. Okay. So we're going to write down, now we're going to write down the mean and the standard deviation from our sample means down here in the lower right corner. And we're going to write down what we got. So my mean was 14.48. My standard deviation was 6.15. And my shape. So what do you think my shape is down here? Is it very skewed right, slightly skewed right, normal, skewed left, slightly skewed left, very skewed left? What do you think? Yeah, it's very skewed right. Okay. Very skewed right. Now, that is not surprising because, when we had our normal distribution and we, did a bunch of samples, we got a normally distributed sample means shape. Now I have a skewed right population, and when I did a bunch of means, I did a bunch of samples, size 2, my resulting sample means is skewed right. So that's not surprising, okay? So, but let's keep going and let's see what happens. Okay. So we're going to increase our sample size to 5 now. So we're going to click right here. We're going to change this to 5 and hit 1,000 times and write down what I get. So I got a mean of 14.68. I got a standard deviation of 3.83. And I somehow screwed that up. There we go. What kind of shape do you think I have? So my options are very skewed left, slightly skewed left, very skewed right, slightly skewed right, or normal. So slightly skewed right. Okay. Some people said slightly. I don't know. It's kind of medium skewed right, but that's not an option. So if you put very skewed right, that's fine. I'm good with that. If you put slightly skewed right, I'm good with that. I don't know. I guess I'll put slightly skewed right. I don't know. Maybe I'll put very. I don't know. All right, let's keep going. Let's do sample size of 10. And we'll hit 1,000 times. And I'll put 14.73. My standard deviation is 2.88. And this one's not as skewed as the other two, so I think this one's slightly skewed right. I'm going to pause here for a second because something weird is happening. As our sample size increases, this distribution down here is less and less skewed. So we're going to do it one more time. We're going to do 30. And 30 is the magic number. So if I put my sample size at 30 and I hit reset 1,000 times, we'll write down what I get. And my mean is 14.71. My standard deviation is 1.58. But my shape, what do you think this shape is? Nathan says normal. Maybe it's slightly skewed right, maybe not. But remember, we said that it doesn't need to be perfectly symmetric for it to be normal, right? So I think that this is normal. And that is a surprising result, okay? Because my original population up here was a mess, right? This distribution up here was very skewed right. I have, maybe this is a population of the average income of people in the US. So you got some people at zero, right? They're unemployed. You got a lot of people in the middle here on the left side. But then you've got this long tail to the right where you've got your CEOs and your basketball players and people making millions of dollars, right? So when I look at this distribution, we've said before that when you have a skewed population or skewed data set, you shouldn't be using mean and standard deviation. You should be using median and interquartile range because they are resistant to skewing, right? We are going to be abandoning median and interquartile range for the rest of this class and using mean and standard deviation. And that's because of the central limit theorem, which says it doesn't matter what shape your population is. If you take a big enough sample, 30 or more, if you take a big enough sample, then your distribution of sample means is normal shaped. Okay. Which I don't know. Like I said, you guys probably don't care. I'm excited about that. That's cool, right? That's counterintuitive. That's surprising to me, right? That doesn't matter what your shape is, you still can use a normal curve, okay? And what's good about that is that means that we can use all of the stuff that we learned in chapter 7 about the normal curve when we were looking at StatCrunch and we did stat calculators normal, right? And we can use that to look at z-scores and look at x-scores and x-values and calculate probabilities using that normal calculator. So there's other things that this theorem is going to allow us to do in chapter 9 and 10 when we look at confidence intervals and hypothesis testing, okay? And we wouldn't be able to do that if this shape down here wasn't normal. Now, you'll hear me say a lot of times throughout this class that the higher your sample size, the more accurate your results will be, okay? I'll say that over and over. Now, 30 is the lower limit. 30 is the magic number. You got to be higher than 30. But if you're at 30, it's still not necessarily perfect. Like maybe you can say like this is a little skewed right because of this tail here. So you'd be better off if you were looking at like a sample size of 50 or 70 or 100, okay? Because if I did that, then my sample means distribution is going to be even more normal shaped, okay? So anyway, uh, so just like with the Pythagorean theorem, which is a very important theorem in geometry, Pythagorean theorem is a squared plus b squared equals c squared. And you can use that for lots of different things in geometry, okay? You can use it for triangles and circles and rectangles, but technically it only applies to right triangles, okay? Same thing with the central limit theorem. You can use it for a lot of different things, but it only applies under certain circumstances. Your sample size has to be big enough. Okay, it has to be more than 30. Okay, so anyway, that all said, let's go back to our project. You know me, I always go on tangents, and you're like, just do the project, Joe. All right, part 2C. For this bell shape, oh, it's not bell shaped anymore. That's a typo. Sorry about that, guys. For this skewed population, right? The population is skewed. What happens to your means as your sample size goes up? So my means here, I had 14.4, 14.6, 14.7, 14.7. Mine didn't decrease, right? 14.4, then 14.6, that went up, and then it went back down. So looking at your means, yeah, they stay roughly the same. Yeah. So my means are going to stay roughly the same. Okay. Chris was like, okay, they fight. Uh, part 2D for the standard deviation, though, I went from 6 down to 3, down to 2, down to 1.5. So yeah, these decrease significantly. Yeah. All right, for this skewed population, what happens to the shape? So I went from very skewed right, and as we went, it became more and more normal. So as sample size increases, the shape becomes more normal. Okay. And that is what the central limit theorem in chapter 8 is talking about. It's saying that if your sample size is big enough, you can treat your sample means as a normal distribution. All right. um, okay, so part 3 is very much the same as part 2, except instead of a skewed right population, we're going to do a skewed left population. So it's the same steps. You'll make a skewed left population by left clicking your mouse and dragging it all over the population. Need to be mean and median need to be 2 points apart. So Let's come back over to here. You're gonna reset and left click, and now I want a big tail to the left. I want a big tail to the left, and then a big bump over here on the right, and that's what you want, okay? So my mean now is 32.7, my median is 38.5. That's a difference of 4.8. So yeah, I'm good. That'll work. Okay. We'll reset our sample size to 2, right? And so, if I ran this with 2s a bunch of times, I'm going to get a distribution that should end up being still skewed left, right? So I'm going to run that 1,000 times, and yeah, this is still skewed left. So, uh, I'm going to write, oh, sorry, I forgot to write down my population mean. Population mean is up at the top, 32.75. Median, 38.55. And standard deviation, 10.94. So that's at the top. And then I skipped ahead already. Sorry about that. So you run it 1,000 times. So reset, do 1,000 times, and then you're write down the mean, the standard deviation from the lower right corner here. So this mean is 33.16. Standard deviation 7.62. Shape very skewed left. Okay. So at this point, you guys have been doing this. You're like, okay, I can fill out the rest of this table. Like, I don't need to watch you do it, Joe. So, I mean, I guess you can if you find that fun, but yeah, sure. So I'll keep going. I'll fill out the rest. So, but you guys don't need my help at this point. Just fill out the rest of your table for 5.77. Slightly. I think mine is slightly skewed left this time. And then 10. And then 32.83. Standard deviation 3.49. Slightly skewed left. All right, and then 30, the magic number, is going to give us 32.7, 4, 1.97, and normal. All right, looks normal. Looks good. Okay. So I'm feeding along 3C, going to get the same answers that you saw before. What happens to the means? I have 33, 32.6, 32.8, 32.7. So those stay roughly the same. This is, I know I'm kind of speeding through this, but this is also an interesting result that your means stay roughly the same. So my mean of my population is 32.75. Okay, at least mine is. Okay, maybe yours is different. But you'll notice that we said earlier that you can't measure the population for, like, if we were looking at like all the people in the US, it's too big. It's going to cost too much time and too much money to measure everyone. So you do a sample. When you do a sample, you can use the means from that sample, and it's not going to be exactly the same as the population, but it's going to be really close. Even with only a sample size of 2. Well, actually, I mean, I did this 1,000 times, so it's a sample size of 2,000 people. 2,000 people is not that bad to survey. And so my mean of 33 is very close to my mean of 32. And actually, when I got to a sample size of 30, my my sample distribution mean was 32.74, which is dang close to the population mean of 32.75. Okay. So why that's good is because you don't need to measure the entire population. You can get really close to what the actual mean is by using a sample. Okay. So anyway, now our standard deviations decreased significantly. Okay. And we've been mostly talking about the shape, right? That's what I've been most excited about, which is as the sample size increases, the shape becomes more normal, right? But we haven't talked about these other ones. So the mean, I said a second ago, it stays roughly the same, which is good. It means you can use a sample to uh, estimate what the mean is for the population. Now, for the standard deviation, though, the standard deviation is decreasing every time it's been decreasing. And the reason for that is the standard deviation of your sample means is not the same as the standard deviation of the population, okay? They are related. The standard deviation for your sample means shape, the one down here, the green, this standard deviation actually has a special name. It's called the standard error. Okay. And the standard error, there's a formula for it. We'll talk about it on Thursday when we look at the Chapter 8 review. But the formula for it is you take your population standard deviation and you divide by the sample size. You divide by the square root of the sample size. But anyway, you divide by the sample size, which if you divide by a large sample size, the bigger your sample size, the bigger the number in the denominator, which means you're going to get a smaller and smaller standard error. Okay. So that is why the standard deviations keep going down. Okay. It's because of that formula. Okay. So anyway, not that you care about that, but that is why that's happening. Okay. So we'll talk more about that on Thursday when we actually do some calculations on standard error. Last part, putting it all together. So putting it all together, again, so the central limit theorem says it doesn't matter what your shape is. You could have a universal, or sorry, not universal, but a uniform distribution. A uniform distribution is where all the heights are the same, okay? And if we run that 1,000 times, your uh, sample means distribution is still normal. You could have some kind of roller coaster thing up here, and it doesn't matter what the shape is for your original population, your sample means distribution is still normal. And that's what's cool about it, okay? So anyway, so let's wrap it up by looking at for all population distribution types, regardless of what shape it is, skewed left, skewed right, roller coaster shape, whatever shape you want to make. How does increasing the sample size affect the means? How does it affect the standard deviations? How does it affect the shape? So as sample size increases, the means stay the same. The standard, I can't spell, deviation decreases, and the shape becomes more normal. Okay. So that's the end of our project for today. So we're going to share in the
Don't do that
upper.
yet, Joe. Don't do that yet.
Don't share. Okay. Okay. All right. Well, that's fine. Yeah, I mean, you guys know how to share, right? We've done this before. So, when you share, uh, you change your general access to anyone with the link, copy the link, right? Same thing we've been doing this entire last couple of months. Okay. And then can I jump over to Canvas now?
Yeah, you're good.
All right, so we jump over here to Canvas and we will, I gotta view a student. What? What? Trying to submit the project. There we go. All right, so you click web URL, paste your web URL in there, hit submit assignment, get your confetti. I got butterflies, no shamrocks. All right, and that's it. Um, okay, so if you have questions, stick around. Otherwise, have a happy sorry, not Thanksgiving. Have a happy St. Patrick's Day, and I'll talk
Happy
to you later.
Thanksgiving.
Oh my goodness. Happy St. Patrick's Day.